Hello everybody, this lesson is going to be about periodic trends. That's a fancy way of saying patterns that we can find on the periodic table. There is a note-taking sheet to glue into your notebook for this if you would like it. It just has some boxes to help you capture the information and make sure you have all the bits and pieces that you need. So the first trend that we're going to learn about is going to be atomic radius. And you've probably heard the term radius in your math class, so you probably have a decent idea of what that means. But what we need to know is how does that apply to the atom? There's a complication with the structure of the atom that makes finding the radius difficult. So in a perfect world, we would measure from the nucleus in the center to the very, very edge of the last filled orbital, which is we call the valence orbital. The problem, though, is if you remember, the orbitals are not tangible objects, and they're also just a probability of where the electron might be. It doesn't mean that is where the electrons are. So we have a bit of a problem. We can't measure to something that's not tangible. So what we end up doing instead is we bond two elements together, and then what we do is we measure from one nucleus to the other. And because those are tangible objects, we can easily measure those. We know for sure where those two things are. Then we can just cut that distance in half and we call that the radius. It may not be perfect, but it is consistent, and that's something that's important, is that we're working with numbers that we know will be true each time we do them. There are other ways to measure the radius, but this is kind of the classic way. This is the way that really shows that you understand that these orbitals are not tangible and that it makes a problem with measuring the radius. So next, what's the pattern? I'm going to show you some actual numbers for these radii so we can see how they go. So we have hydrogen, lithium, potassium. As we go down a group, and then here we have sodium, phosphorus, chlorine, as we go across horizontally across a period. So you can see as we go down the group, what happens? Does it get bigger going top to bottom or bottom to top? Well, you can clearly see based on the numbers that the radius is going to get bigger as you go from the top of the periodic table to the bottom. That should make sense to you, right? You're adding energy levels. Potassium's a lot bigger than hydrogen. Potassium is in energy level 4 compared to hydrogen in energy level 1. So that seems to make sense. But when you look at this one, things get a little complicated. When I go from sodium to phosphorus to chlorine, look what happens to my atomic number. I get more and more protons. I get more and more neutrons also. I also get more and more electrons. But look what happens to the radius. It ends up smaller, doesn't it? That's kind of counterintuitive. That's a little strange. So my radius actually gets bigger going right to left, which is a little bit different than what you probably expected. One of the ways that I like to summarize this is by drawing a big rectangle to represent your periodic table. You don't have to draw, all the little steps. Just draw a big rectangle. It's going to get bigger going down, and it's going to get bigger going to the left. So I'm going to put one big arrow going across, going from the francium corner, from the fluorine corner up here down to the francium corner. Fluorine is really tiny, francium is really big. Next, we have to stop and think about why is this the pattern we have. We're going to look at the pattern going up and down a group and then side to side across a period. There's going to be a little bit more words on this slide than normal. It's a concept that in order to explain it, it takes a little bit more what we call verbiage, right? I have to use a little bit more words that I normally like to use in a chemistry class. But once you get the concept, you should be able to just quickly jot down a little bit of what you see on the slide. Please don't try to copy everything word for word. Remember, you could always go back and rewatch the video, or you can always go back and look at the PowerPoint again. So, why does it increase going down a group? This is the one that we have a pretty good understanding of. You're adding more energy levels. The problem is that's kind of a middle school level answer. We need to go a little bit further than that. We need to explain why more energy levels results in a bigger radius. Why can't these levels just coexist at the same size, the same place, right? So the reason the higher energy levels end up further and further from the nucleus is because the inside level of electrons are going to shield the outside electrons. If you look at this little cartoon down here, we have the nucleus pulling on the electrons over here. Here are the valence electrons on the outside, and all these inner core electrons are kind of shielding it. That means that the nucleus can't pull as hard on these valence electrons. It weakens their ability to pull them in closely. And if they can't be pulled in closely, then that means the radius will be bigger. We also have a little bit of repulsion between these electrons as well, don't we? They don't all want to crowd together. So that's another aspect to think about. So you can see that we get, as we go out and get more energy levels, these inside ones are going to shield the valence electrons so the nucleus cannot pull them in as tightly. Going across is a little bit tricky. So let's think about this as going left to right. It's going to be a little bit easier to explain because it kind of is going to explain the bit that is counterintuitive. So as you go left to right across a period, you're adding more protons, you're adding more neutrons, you're adding more electrons, but the radius gets smaller. The reason is that the protons are going to pull harder than the electrons can. And so the more protons you have, the more they can pull in the valence electrons to make a smaller radius. We are not adding extra layers when we go across a period. We do not have extra energy levels as we go across a period. All the electrons are being added to kind of the same area, right? And so as you go across, you add a proton, you add an electron, but the proton's effect is going to be stronger. I like the analogy of if you're playing tug-of-war and you have a bunch of football players on one side and on the other side you have a 2-year-old. If you have 3 people on each side, yes, you have equal number of people, but the football players are probably going to be stronger, right? If you add a 4th person to each side, yes, you're adding 1 person on each side, but your addition of the football player is adding greater strength than the addition of the 2-year-old. So the proton is like the football player and the electron is like the 2-year-old. It's a 1-to-1 addition as you go across. When you go from sodium to magnesium, you add a proton, you add an electron, but magnesium is going to end up smaller because the proton has more of an effect. And it's going to pull that electron in closer, making the radius smaller. So the phrase we use, kind of a vocab term, is we say that as you go across and as you add a proton, you get a greater effective nuclear charge. The nucleus is going to behave stronger. It's going to have a bigger effect, and that's going to result in a smaller radius. The next trend is something called ionization energy. So we know the term ion, right? Ion is something that does not have the right number of electrons to proton ratio. So we are going to look at this from the perspective of trying to remove an electron. How much energy does it take to take an electron away? If you have a high ionization energy, it means it really, really wants those electrons. It's holding on to them really tightly. Okay, it's going to take a lot of energy to take one away. If you have low ionization energy, the electrons are not being held onto by the nucleus very much, so it's very easy to take them away. It takes a little bit of work, but not a lot. So let's look at the definition, okay, the what is it part. The energy required to remove an electron from a neutral atom. In other words, how hard is it to take an electron away? The more energy it takes, the harder it is. The stronger it's being held on to, the more energy it takes. The stronger that nuclear attraction is, right, the harder it will be. So let's look at the pattern. So what is the pattern? Here's some data once again. We're going to use the same elements. As we go down the group, right, this time it's backwards, isn't it? So if I ask you which way does it increase, this time it's going to increase going upwards. And if you look at this one, which way does it increase? Well, it's going to increase going to the right this time. This is the opposite pattern, isn't it, from the radius? The radius got bigger as you went down towards francium, but ionization energy is going to get bigger as you go up towards fluorine. So you can draw a big rectangle to represent your periodic table, and you're going to point a big arrow going that way. One thing you need to add that's really important is that the noble gases take so much energy to remove an electron. They are the highest on the list. Noble gases do not want to let go of an electron at all. They're perfect, aren't they? So if they're perfect, they are not going to want to let go. You're going to have to put a lot of work into taking one of those electrons away. The elements down here that are not colored in is because these things are typically very radioactive or very, very rare, and they may not have a value for it. So make sure you write down somewhere that noble gases are the highest. So let's think about why this is the pattern we see. We're going to increase left to right because we know that we get a smaller radius, so we have a bigger effective nuclear charge, which means the nucleus is holding on to the electrons tighter, which makes it harder to take them away, right? And so if those electrons are so close to having a valence shell, they don't want to get rid of those electrons, do they? So they're very close to being stable. They're getting smaller and smaller as you go to the right, so their electrons are being held onto tighter and tighter and tighter and tighter, so that ionization energy goes up, 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 up. Fluorine takes a lot of energy to take an electron away from. Francium, totally easy to take one away. Francium is huge. It doesn't have much of a pull on those valence electrons. So it increases going upwards this time because as you go up, you have less shielding, so the nucleus is stronger, right? Those electrons are closer, so they're being held onto really tightly, so they're harder to take away. So hopefully you can start to see that all of these answers really have to do with how the nucleus interacts with the electrons on the outside shell. The bigger it is, the weaker that attraction. The smaller the atom, the stronger that attraction. And that affects all these patterns that we start to see. The next trend is going to be something called electronegativity. So if ionization energy was measuring us taking an electron away from an atom, electronegativity is measuring how hard is that atom pulling on somebody else's electrons. If it's in a bond, how hard is it pulling? Is it trying to attract the electrons or not? So electronegativity, kind of the fancy definition, is a measure of the ability of an atom in a chemical compound to attract electrons from another atom in the compound. In other words, how strongly can that atom pull on the electrons from another atom? Is it tugging really hard, or is it not tugging very hard? So let's look at the pattern. We're going to skip the data this time. We're just going to jump straight to the arrow. I just like showing you the data once in a while to get you to see, there are actual numbers for these things. I don't just make it up, right? But let's just jump to the big arrow across our periodic table. Draw your rectangle for your periodic table. And you're going to see that our arrow points up towards fluorine. That makes sense. Fluorine is very tiny. It can pull very, very hard. Francium is huge. The nucleus does not have a big pull. The valence shell is super far away. It can't pull very hard. One thing that we have to make sure we know is that this time noble gases are the lowest. They don't want to attract the electron, do they? A noble gas is totally stable. It does not want more electrons. It's not going to try to attract any. So ionization energy, the arrow points the same way, but noble gases are the highest. Electronegativity points the same way, but noble gases are the lowest. This is one of the most commonly missed questions. If I ask you to start ranking elements, people forget that the noble gases have to be considered separate. You got to think about them separately, so be a little bit careful with those noble gases. So let's look at why. Why is this the pattern we see? Well, we increase left to right because we have a smaller radius, so we have a greater effective nuclear charge, so the nucleus can pull harder, right? And also realize, right, they're getting really close to being stable. All of this results in higher electronegativity. Once again, you can see that our reasoning is related to the size, because that's going to explain the strength of that nuclear attraction between the nucleus and the valence electrons. Increases going from the bottom to the top because we have a smaller radius. This time we have less shielding, right? We don't have as many energy levels at the top, which means that nuclear attraction is stronger. It can pull harder, so we get higher electronegativity. One of the things that is hard about this chapter is it feels overwhelming, all these different trends and all these arrows and ranking things big, small, or small to big. But if you think about the fact that this gets repetitive, that we end up with the same types of answers over and over, think about the size. Think about if you have more or less energy levels. Think about how strong the nucleus is. Think about, can it pull hard or not so hard, right? Those are going to get you to the right answer every time. The last one is kind of the result of all the patterns we've seen. Reactivity is going to be the result of all of those other things. So what is reactivity? Reactivity is going to describe the type of reaction and the size of the reaction. Is it a big reaction or is it a small reaction? So elements in the same group are going to have the same types of behaviors. Remember, that's why we call them a family. People in a family may not be identical to each other, but they may have some characteristics that are similar. You may not look exactly the same as your mom or dad, but you may have some features that look similar, or maybe some behaviors that are similar, right? Some mannerisms. The reason why this is true for elements is because if they're in the same group, they have the same number of valence electrons. Because the valence electrons are the ones participating in the reaction, they're the ones on the outside. That means if they all have one valence electron, they can perform similar types of reactions. If they all have 7 valence electrons, they can perform similar types of reactions. The big difference, though, when it comes to reactivity is that the magnitude of the reaction may be different. One reaction may be really small, maybe it's just some little bubbles that form. But another one may be so big that it explodes, right? So the magnitude, the size may be different. So what is the pattern? This time we're not going to have an arrow going all the way across the table because it depends on which class of elements we have. Remember that we have metals and nonmetals and metalloids. Well, metals are more reactive as you go down, and nonmetals are more reactive as you go up. And then another thing to think about is this time the noble gases are the least reactive, right? They are not going to have much of a reaction. They're already stable. They don't want to react because why would they make themselves worse off than they already are? If you look at the periodic table, the alkali metals are the most reactive metals, and then would be alkaline earth, and then transition as you go this way. So the furthest to the left is the most reactive metals. The halogens over here are the most reactive nonmetals. And then once again, those noble gases do not like to react. They are inert. So now let's think about why do we have this opposite pattern? Why do the metals and the nonmetals behave differently from each other? So for the metals, they get more reactive as you go down because it's easier to lose electrons as you go down. Metals want to make cations. They want to make a plus charge. Well, if they have a bigger radius as you go down, you get more shielding as you go down. Your valence electrons are further away as you get down. You have a lower ionization energy as you go down. That means it's easier to take an electron away, which is going to mean the reaction is going to be big and it's going to be fast. The easier it is, the bigger the reaction. So as you go from lithium to sodium to potassium to rubidium to cesium to francium, all these things, right? You get bigger radius, more shielding, you get further away, makes it way easier to take an electron away, and so you get a bigger reaction. Now, if you think about the fact that the nonmetals want to make anions, the nonmetals want to gain an electron, that's going to explain why we have the backwards pattern. If metals want to lose an electron and nonmetals want to gain an electron, they're going to have backwards pattern. So nonmetals are more reactive as you go up. It's easier to gain electrons because you have a smaller radius, you have less shielding, you have higher electronegativity, so it's easier for the nucleus to take an electron away from something else. it's easier for it to become a minus charge. Okay. If you're interested, there are some 2 videos here that you can watch. The links you can get in the PowerPoint. The Brainiac video is a British TV show, and it's a little bit silly. They're always really goofy and make weird comments and things. What they're doing is they're dropping different metals into water and seeing the size of the reaction. One thing to know is that they kind of faked it a little bit. They augmented the reactions so that they looked bigger and more impressive. And so for me, I feel like as long as you know that, I'm okay with you seeing that video. I think it's memorable, which is important. I want it to stick in your brain. So just make sure you know that they kind of made the reactions a little bit bigger than they would be, so it'd be more impressive. The other one, the disposal of sodium, is an old video. It's black and white. It's from World War II. They used sodium in the war to make bombs, and afterwards they had a ton of sodium left, and they had to dispose of it. And so it's showing how they disposed of that sodium. And you can see when it reacts with water how it reacts. And the way they dispose of it back then is not something we were allowed to do anymore. They literally dump it in a lake. And so it's kind of crazy to see them do something that we would never be able to do these days. You can't just go dumping chemicals in lakes anymore. All right, I would like to do a couple little practices. Try to rank the radius of those elements from small to big. Try to rank the ionization energy of that next set of elements from small to big. And then you have some reactivities I'd like you to rank. Keep this group together and rank them, and then separately rank these. And everything's going to be from smallest to biggest. Pause the video, give it a try, and then unpause and you can see the answers. All right, so if we look at the periodic table, fluorine is in the top right corner, so it's going to be the smallest. Then as I scan the periodic table and I look for my other elements, I'm going to notice that aluminum comes next. It's a little bit to the left, and it's a little bit further down, so it's going to be a little bit bigger than fluorine. And then potassium is all the way to the left, so that will be the biggest out of that set. Ionization energy is going to have the opposite pattern, right? The smallest is going to be in the bottom left corner, and the biggest is going to be in the top right corner. So when you look for these elements, you're going to see that barium is in the bottom left. As I scan the periodic table, I'm going to notice, well, calcium is above it, so that makes it a little bit higher. And then sulfur is all the way in the right top corner, so that will have the highest ionization energy. For reactivity, we have to remember that metals and nonmetals are different. The first set is a bunch of metals. So metals are going to get more reactive as you go down. So if you find these on the periodic table, manganese is number 25. So that one will be the least reactive. Then we have technetium, and then we have rhenium. As you go down, they get bigger, easier to lose an electron. The last set are nonmetals, so they're going to get more reactive as you go up. So if you look, selenium is going to be at the lowest point, then we get sulfur, and then oxygen is in the top of that column. So that would be the most reactive out of that set. Okay. So last slide is just a really quick recap. When you're going up and down a column vertically, your shielding is going to change due to the energy levels, and that's going to kind of result in all the patterns you see. When you go side to side, your effective nuclear charge is going to change because you're adding or having fewer protons depending on which direction you go. And that's going to result in all the patterns you see. So it's really important that you kind of keep these two little bullet points in mind. If it's an up and down question, think about the size of the energy levels and that shielding effect. If it's a side to side question, think about the number of protons and how that will change the size and how that will change all your patterns. Your radius gets bigger going down to the left. Ionization and electronegativity increases going up to the right. For reactivity, metals increase going down because they want to lose electrons. The nonmetals increase reactivity going up a column because they're trying to gain those electrons. All right, I know that feels like a lot. It's probably one of the longest lectures we do all year. It's one of those things that takes a lot of work to explain it, but then once you start ranking the elements from small to big on various patterns, it becomes a little bit easier. You start noticing that your answers get very repetitive. You start talking about shielding, or you start talking about effective charge over and over and over again. We're going to do a bunch of practice. We have lots of worksheets on this. We have a lab on this. So by the time we get done with all that practice, you'll realize that it took a lot of words to explain something that will just come back to the idea over and over of how strong is that nucleus pulling on the electrons. That's all this is. It's just a lot of words to explain something that will feel a lot simpler in a week. Okay? All right, everybody. I hope that was helpful. Bye.